So, good morning everyone, and as promised before or as planned before, we will cover this classical control topics in a very quick way, some sort of an overview before we move on to the modern control topics. So, next couple of lectures will be kind of some sort of an overview of classical control systems. May not be in very detail, but I assume that this particular audience have some knowledge of classical control systems already. So, that will kind of help us moving these topics rather in a fast way. First thing before we talk about any classical control system is a review of Laplace transforms. So, let us see what does that transform do. So, Laplace transform of any function f of t can be defined as something like this. It is an integral from 0 to infinity, strictly speaking 0 minus. So, just about little bit before 0, this integral f of t to the power minus s t dt, and s in general can be a complex variable which has some sigma is the real part and omega is the complex part of it, I mean omega is the imaginary part of it. So, when you have this Laplace transform, once you take Laplace transform of a time varying function, essentially it gives us some sort of a frequency dependent function, where s can be treated as some sort of a complex frequency. Then suppose we also have f of s already known to us, then we can talk about inverse of Laplace transform. So, essentially we are attempting to get back this f of t. And the very fact that these two functions are uniquely defined for t greater than 0 makes our life much easier in especially in linear control systems, especially classical control system. This little u of t what you see here is something like a step in unity step input defined from t equal to 0 onwards. Before 0 it is 0. So, we are mainly interested in positive time sort of response in this inverse transform, inverse of Laplace transform. And that is what mainly we are we are bothered about in control systems for t greater than equal to 0 anyway. So, common test signals used in control systems as we know are so roughly this one thing can be treated as something like a step input, that is a step, okay, with a t and something like f of t, just a constant number, and typically this is unity step input. Then we have this ramp input, okay. So, this is t and this is f of t, this is ramp, okay, and then there can be let us say parabolic, okay, f of t is equal to typically t square or t square by 2, okay. So, this is the ramp input, sorry, this is parabolic, okay, and we also can use something like a sinusoidal function for sin omega t sort of thing in many applications. So, and the reasons for choosing these functions are like this. Suppose you have any continuous function, then we can have something like a Taylor series expansion, then this constant function pops up first, and then there is a ramp input. So, that is this like t sort of thing. So, you have this Taylor series f of t is something like a0 plus a1 t plus a2 t square by 2, like that actually. So, you have this at least one sitting here. So, if you see this functions 1 t square by 2 and things like that, and if you really test some function with respect to these three signals, then at least up to first 3 terms we have confidence that things are okay. So, primarily when you see this step input, you have this transient response as well as steady state, but ramp inputs are primarily used for like steady state errors and parabolic as well sort of thing. So, there will be something like that, and there are various reasons for that. Why do you need to test for all these signals actually? Sinusoidal again similar way, it is used both for transient response and mainly for steady state response. If you see this will continue like this, and then it is also used for modeling actually, like system identification. For example, if you give sinusoidal input, then you can talk about what frequency it can respond and things like that. So, there are various utilities, not necessarily only in transient response sort of things, transient and steady state response, but there are other applications as well. Sinusoidal function similar way, the same function you can decompose that in Fourier series, for example. Then you will sine and cos terms will pop up actually. So, if you are interested in decomposing a function in Fourier series way, and try to interpret whether my system is behaving well or not, then sinusoidal test signals are very useful actually. Now, let us see how do you take Laplace transform. First thing is one example where you let us talk about okay, this is t to the power n. So, you have this this standard definition e to the power minus st into t to the power n dt. So, you introduce change of variable v equal to st. So, dv equal to s dt sort of thing, and then you go back to this integral and see what all e to the power minus st will become minus v, then t becomes v by s, like that. Then 1 over s to the power n, and then there is one more. So, there n plus 1 will come out here, and then you have this this particular integral what you see here is can be shown as n factorial by induction. Okay. So, then it essentially turns out n factorial by s to the power n plus 1. Similarly, example 2, if you see e to the power t, then again you plug it back in the definition, and then you carry out the algebra. This is rather fairly straightforward. You have s minus 1, so it is s minus 1 t e to the power minus of s minus 1 t divided by minus of s minus 1. Evaluate it from 0 to infinity, and then you are left out with this one, and that at infinity this is 0, e to the power minus infinity sort of thing. At 0 this becomes 1. Okay, so 0 minus 1, essentially you are left out with 1 by s minus 1. So, that's the way to kind of see these functions, how these functions are popping up from time domain function to frequency domain thing. We cannot keep on doing every time like this. They cannot keep on plugging to the formula and then get some results. So, there are standard tables available for various standard functions. For example, if you consider this impulse function, then the f of s has already been evaluated as 1, and this is 1 actually. So, 1 into u to the 1 into ut. So, you have essentially 1 over s. This ut is the same ut that you have discussed some time back. This is this kind of a function. If it is greater than t is greater than 0, then it is 1. If it is t is less than 0, it is 0 really. Okay. So, that helps us in the algebra part of it actually. So, this one we have already shown. This is some of these we are going to show it also basically. Okay. So, these tables are available. This is rather a limited table, but extensive tables are also there, different functions and things like that. But these 6 or 7 functions can be like some sort of a basis function sort of idea, that using these functions you can do many algebra actually. Then there are further ramifications. So, that means suppose I mean this is by definition anyway, then suppose you multiply by k, just a constant, then this k pops up. Simply from this definition you can see that it will come out of the integral, and similarly f1 plus f2 will satisfy this. So, these two together will tell us that this Laplace transform is actually a linear operator. Okay. Then if you have e to the power minus at into f of t, then it turns out to be that f of s plus a. So, this is something called as frequency shift theorem. Then there are time shift theorems, there are scaling theorems available and things like that. What is very useful in our control system analysis is this part of it. When you have df by dt, then it is just into f of s minus f of 0 sort of thing, and then d square by df dt square, I mean up to nth order you can do, no problem. Whatever is the order, it will satisfy the same thing. But remember, this side of the story, these are all time domain initial conditions actually. So, we will see that actually as we go along. And there is integral theorem also, that if you take integral of a function, then talk about Laplace transform, then it turns out to be just divided by s. So, what this Laplace transform essentially do? I mean, if you see this this derivative, so derivative operator essentially turns out to be a multiplication, integral operator turns out to be a division. That means this this differentiation and integration, which are rather little complex operators in time domain, they turn out to be simply algebraic manipulations in the Laplace domain. That is the great simplicity that it brings in actually. So, further analysis and all, it becomes easier actually. So, then there are theorems like final value theorem and initial value theorem. That means you really do not have to do, once you know the f of s part of it, and you want to find out what is this like when t goes to infinity, what is the value of the function, that is essentially the steady state value. Then you do not have to do like inverse of Laplace transform and then see what is going on at t equal to infinity as a limiting case. Instead of that, you can just use this this limiting value theorem, I mean this limit rules and all that. So, you just take s tends to 0, s into f of s, that is it actually. And similarly, when you talk about initial value theorems, then you do the other way, like s tends to infinity s s into f of s. And these theorems are not universally true, rather, there are some conditions available. So, for example, this final value theorem, all roots of this denominator of f of s must have negative real parts and no more than one at the origin. That essentially tells us that this function what you are looking at has to be a stable function. We will see the stability theorem slightly later actually. And similarly, there is a condition for theorem 2 also basically. Now, let us go back and try to justify some of these theorems. For example, see if you want to see how this one is coming up, because 2 and 3 are very easy to see that from 1. Now, for 4, if you just go back to this, then this is by definition e to the power a t and things like that. So, this is simply from definition. This is Laplace theorem, the integral definition. Then you combine these two and then interpret some s hat as s plus a. There is some sort of a change of variable actually. Then Laplace transform of e to the power minus a t into f of t, that is what you are considering here. It turns out to be simply e to the power minus s hat into f of t dt, and that is again by definition f of s hat. That is simply by definition. So, what s hat is s plus a. So, essentially it tells us that this is nothing but this f of s plus a. So, this is as simple as to kind of show that actually. It is not very difficult to show that at all. Example, so we already know that sine of 2t is this one. Using this table you can see that probably. Okay, the sine of omega t is omega by s square plus omega, that also can be derived by the way. So, when you know that the sine of 2t is this like this, so you really do not have to do one more time the moment e to the power minus 3t pops up actually. So, you simply use that formula, that result. So, it is s2 and wherever s is there you replace by s plus 3 essentially. So, you carry out with and this transfer function results in that way. Similarly, if you have cos 2t instead, then this transfer function is like that. And then if you have e to the power minus 3t, then wherever s is there you simply replace it by s plus 3, that is the theorem actually. So, this results in that kind of a transfer function essentially. That kind of a Laplace transform. Now, there is another result which tells us that e to the power n f of t is this one. It is also not that difficult to solve. So, we will start in a rather reverse way. So, this is f of s, this is again by definition. So, then if you take derivative, then this derivative goes inside, because this integral is with respect to time, remember that. So, s is actually a independent variable of the integral. So, it goes inside, and then you do, and then this f of t is not a function of s. So, you can take out and then take derivative with respect only with respect to s sort of thing. Okay. So, t sub some sort of a coefficient here, it is minus t e to the power minus s t because of that, and then this one. So, minus 1 taken outside the integral, then you are left out with that kind of a thing, and this by definition is Laplace transform of t f of t. So, if you rearrange the things and tell okay, Laplace transform t f of t is nothing like nothing but this, then I multiply one more time, then consider that is t into that entire function, but that entire function is already available to me. So, I will repeat, I keep on repeating this and then try getting these results actually. So, if I do that n times, then I will have a minus 1 to the power n, and then this nth order derivative pops up actually. So, these are little manipulation in the algebra here and there to which gives us some sort of important results actually. Now, this Laplace transform of the derivative of a function, how does this one happen? Again you go back to the definition part of it, and then this time you integrate it by parts actually. So, this is exponential, this is just another function. So, I take this one times integral of that, which is f of t, minus differentiation of that, which is this one, okay, and then integral of that, which is that one. Okay. So, then this one infinity again, when e to the power minus infinity is 0, then e to the power 0 is 1, then f of 0. So, essentially this s comes out of the integral side, out of the integral minus s. So, essentially we are left out with s into f of s from this part of it, minus f of 0 from that part of it actually. And in most of the situations in a classical control system or linear control theory especially, we will see that it is assumed that f of 0 is 0. And that is primarily because of the thing that we discussed in the first class, that linear system behavior or stability nature is independent of initial conditions. So, that is the fact that I will keep on repeating. So, we will not hopefully forget that. So what it essentially tells us is multiplication by s of a f of s essentially leads to this some sort of an interpretation of derivative. That means the multiplication of s is nothing but a time domain derivative property actually. Generalization, you take double derivative and then repeatedly apply it one more just one more derivative sort of thing. This result is already there with us. Okay, so we just repeatedly use s into this entire thing. Okay, this result is already available minus f dash of 0 because this is f dash actually here. So then you multiply everything, then it turns out to be s square into f of s minus s into f of 0 here minus f dash of 0. So that is how it pops up here. If you do one more time, again this result is now available. So you apply one more time to that minus f double dash of 0. So essentially it leads to some sort of a polynomial like this. So first derivative leads to a first order polynomial, first order s multiplication of f of s. Second derivative leads to s square into f of s, third derivative leads to s cube into f of s, and then if you see the trend, then this s will start diminishing, s square, s cube, s square, s and then s to the power 0 sort of thing, and then this time domain initial conditions will start from 0th derivative f of 0, then f dash 0, then f double dash 0 like that. It's rather easy to remember that way. Okay. Then integral operator, we know this 1 by s. So how do we go about doing that? We again go back to this, and then z of 0 is 0, z dash of t is f of t sort of thing. What we are really doing here is we are just redefining this g of t as integral of that what we are interested in actually. Okay. Then g of 0 is 0 to 0, so that is essentially 0, and z dash of t, when you take derivative here, that is nothing but f of t. So this f of s, which is nothing but Laplace transform of f of t by definition. This part is just definition. Then I substitute f of t as g prime of t, okay, here, and then g prime of t I will use my result which is already known to me anyway, and g of 0 is typically 0, that is what we will assume. Okay. Not necessarily assume, g of 0 is 0 here essentially because of this integral property 0 to 0 anyway. So this is equal to 0, and then we are left out with this term which is s into Laplace transform of g of t, but g of t is by definition this. So if you just see this Laplace transform of this integral is nothing but 1 by s into f of s. That is what you have done here actually. Okay. So division by s is nothing but an integral operator. That's what it tells actually. Alright, so all these results are available to us. So it becomes handy for us to do further analysis of the single input, single output systems, which are of primary importance in classical control theory. So before we move on, there is we'll need to know what is a transfer function of a system. So let us see that. So in block diagram, any system can be represented something like this, very standard textbook material. Many of the textbooks will represent this way. This is like reference input as r of t, and some sort of output as c of t basically, and some books will follow that as u of t and y of t. So depending on what kind of input you talk and what kind of output you discuss here actually. So probably these are commanded output. So C stands for commanded output and R stands for reference input basically. And this system need not be one single unit. This can be a connected subsystems can be there inside this system. So there will be a subsystem 1, 2, 3, and many subsystems are not necessarily connected in a serial way. They can also be connected in a parallel way and things like that. So essentially, what you are interested in is a relationship between input and output. What goes on inside the system, we are not too much keen in this kind of analysis actually, but we are really interested in whatever happens there, can it be represented in terms of C of t, in other words this relationship between C to R basically directly. So this C to R is typically represented in some sort of a polynomial in the numerator divided by polynomial in the denominator. We will be able to see that in a second actually. Okay, how do we get that? Okay, so any physical system, we all know that it can be represented by some sort of a differential equation. However, we are assuming that the system is linear, time invariant, constant coefficient differential equation. That means these coefficients what you have are all time invariant actually. They don't change in time. That's why this when you see this this transfer function, Laplace transform and all that, essentially implicitly we mean that we mean single input, single output, time invariant difference system basically. The order can be high or low, whatever it is, but essentially it is a linear system and it is a time invariant system. It is a single input, single output as well actually. Okay. Anyway, so this is the physical relationship which will give us either from Newton's law or Kirchhoff's law or black box modeling, whatever it is. And then what is this? You are talking about this C of t as nothing but the output and R of t as nothing but the input actually. So, nth order differential equation for the output is connected by mth order differential equation in the input in general. This can be 0th order also, I mean depending on whatever you have. So, what do? You start with this differential equation and then simply take Laplace transform on both sides. So, then what happens? This is nth order polynomial. So, this is a constant of course. So, add a n into s to the power n, then Laplace transform of this C of s actually. So, that is what it pops up here. The next one is like that, next one is like that up to this term plus all sort of initial condition terms. Okay. And similarly, on the right hand side, it is all sort of this polynomial with mth order and then all initial conditions. And again, we all assume that initial conditions are 0. Again, this is because of linear system property that is independent of the exact value of the initial condition. So, the ratio term, then once you take out this one, this initial conditions as 0, then you can take C of s as common from left hand side and R of s is common from the right hand side. So, then C of s and R of s, once you take common from left side and right side, you can talk about C of s by R of s now. So, it will pop up like this kind of a polynomial and that is what we showed here. Okay. See that. Okay. That is what we showed here actually. Okay. So, then this is what is called as transfer function in general actually. Okay. That is why we get that. So, when you talk about system block diagram representation sort of thing and we are interested in output to input, then this is in general this kind of a thing will pop up here. Okay. And one thing to note here is if m is less than equal to n, which typically happens in many systems, then it is called a proper transfer function. And if m is strictly less than n, then it is also called strictly proper transfer function, and these kind of notations are useful in modern control theory as well, especially in robust control theory and all that. And then by definition, the roots of the numerator, that means if you make it equal to 0, the numerator part of it, that will give us zeros, and if you make equal to 0 in the denominator part of it, that will give us poles actually. That is by definition. Okay, now move on to the example part of it. We start with a small example. These examples are primarily taken from Namanais anyway. So, you can see these examples there also. So, this is the kind of a RL circuit, that means you have a resistor and just a this inductor in the loop, and V of t is nothing but your input to the system. So, we know that this voltage drop across R is R times I, and what voltage drop across an inductor is L di by dt, that is from physics part of it, and there is a current circulation which goes on there, and that is nothing but I of t. So, the relationship that governs this system is nothing but the voltage drop across this, which is R times I, plus this voltage drop across that, which is L into di by dt, is nothing but the voltage applied actually. So, our law of conservation of energy will give us that. So, this relationship we already have in time domain. Now, we go to Laplace domain, okay, because we really do not want to deal these differential equations directly as it is in classical control. We want essentially this algebraic representation, so that we can manipulate them easily and things like that. So, we go back to like applying this Laplace transform both sides, then this is V of s is nothing but S into L of s, okay, and plus R times that I of s actually. So, if you carry out the algebra yourself, so okay, let me just quickly do that maybe. So, this is something like V of s in the left hand side is equal to L into S into I of s plus this R into I of s, okay. So, this is L s plus R into I of s. Okay. So, then this I s by V s, that is what I s is our output here. So, that is how we get it here actually, okay, I s by V s here. Okay. Okay. So, essentially if you see the pole location, then you make it equal to 0, the denominator part you make it equal to 0, and hence you get some sort of a pole location at minus R by L actually. That is what we do that. Alright, now that is the first order system. So, little more complex system, we all ride on these roads with a car and things like that. So, those can also be modeled with respect to this input that is coming to the vehicle as some sort of a displacement, that is xi sort of thing, that is nothing but the input to the system, and x0 is the vertical motion of the body, that is what you are interested. So, because there is a suspension system in between, so whatever motion comes to the tires, it does not go directly to the vehicle. I mean, that is how we have some sort of a smooth ride on the road all the time. Otherwise, the ride will be much more bumpier, like some sort of a bullock cart, for example. There is nothing there actually. Okay. So, directly it gets transmitted. So, compared to a bullock cart, a nice car, I mean, a relatively well designed car feels much more smoother on the same road, by the way. So, this is because this xi that goes into the system is not the x0, that is the vertical motion of the entire body. So, how do you take care of that? Because this entire auto body, there is a center of mass, and there are different levels of modeling. You can consider the auto as a kind of a single point mass, that is what we are doing here. But next level of modeling will discuss about how many inputs you have, whether you want to model it in a pitch plane only, that means only in one plane, or you want to take care of all these 4 wheels independently, and then discuss something like a 6-DOF model sort of thing. Okay. It will be like rolling motion, pitching motion, all sort of thing. So, there are different levels of modeling here, and depending on what is your motivation and what you want to do with that. So, here what you are doing here is that this auto is kind of a single entity, there is just a one point mass sort of thing. There is xi to the body, input to the body, and then we consider that as some sort of a lumped mass with lumped spring and lumped damper. So, essentially, it is a spring mass damper system, spring, mass and damper, and we are interested in the vertical motion of the body as x0, output of the system, and input to the system is xi actually. Okay. So, the entire thing what you see here in reality, we can really represent it based on this lumped behavior sort of thing, provided we know these values accurately, k, b and m and all that. But here we assume that these values are kind of known to us, because somebody has done this parameter identification already basically. So, what is this? So, if you go back, then this loss of motion, which is essentially Newton's law, you can draw the free body diagram and things like that, which will give us this kind of a equation basically. Okay. And then this equation I can separate it out, put the input to the right hand side and output to the left hand side. Then I take Laplace transform of this left hand side, which will give me something like this, okay, and the right hand side will give me something like that, and hence the transfer function turns out to be Bs plus k divided by all this actually. Okay. So, that is that's how you see that these transfer functions are derived based on physics of the system from the beginning. Now, this is all about utility. So, if you see this, go back to this, this is what you are looking for, and there are variety of ways to get that, and one primary way to get that is using laws of nature, the physics part of it. Starting from this differential equation, okay, starting from this laws of nature, whatever we visualize here, we will be able to derive this transfer function actually. In that couple of examples I have given you there. Next, once you know the system, transfer function, essentially we want to know what kind of inferences or what kind of conclusion you can get from those transfer functions. And first thing to analyze there is the time domain response of first and second order system, especially with respect to the step input. So, let us say what do you get there actually. Okay. So, system response, I go back to that RL circuit, and RL circuit was here, okay, and now I assume some values for sake of simplicity. I assume that this is V of t is unity step input, that means that is 1, and L and I also I will assume some values here. Okay. So, L I assume that there is a 1 Henry sort of thing, R is 1 ohm and all that, just for our simplicity sort of thing. So, if you go back to that transfer function, it will turn out to be something like this 1 by s plus 2 sort of thing. Okay. And then the pole location turns out to be at minus 2, because the moment you make it equal to 0, s equal to minus 2, that is the pole, and V of s is actually 1 by s, because V of t is 1. Okay. So, then this I of s, if you really plug it back, as that I of s is V of s divided by s plus 2, but V of s is 1 over s. So, 1 over s by that actually. And how to get time domain, time domain solution sort of thing. The first thing to do here is to carry out some proper algebra, and that is done by partial fraction expansion. I have not discussed too much about that. Those of you are interested, you can see in our nice book also. There are various ways of doing that depending on what form you have here, and this particular form gives us independent roots actually, because s equal 0, s equal to minus 2, that is what the roots are. They are independent anyway, that they are not repeated actually. Okay, so they are real and different. So this form turns out to be a by s plus s plus b by s plus 2 that way, and a and b very quickly you can evaluate. A nothing but s into whatever you have here. So, s into this one, that means s cancels out, and that is evaluated at s equal to 0. Okay. So, s cancels out means you are left out with that, and that is evaluated at s equal to 0. And b is similar, this entire function multiplied by s plus 2. So, that this will go from numerator and denominator, they cancel out, and then you have to evaluate that at s equal to minus 2. That is what you do here. Okay. So, a turns out to be 1 by 2 and b turns out to be minus 1 by 2 actually, and then you plug in back here, that is I of s is 1 by 2, I mean 1 by 2 divided by s, divided, this is nothing but minus half divided by s plus 2, and we take the inverse Laplace transform using the results that we already have, and this one will give us 1 by 2 into 1. Okay. And this will give us like 1 by minus 1 by 2 into e to the power minus 2t. Okay, into 1 is there anyway. So, that is what it is. So, this part is essentially forced response, and this part is essentially natural response, and directly solving in the time domain we discussed in the last class anyway. You can also solve this using the differential equation, the first order differential equation, time invariant and all that. So, you will essentially arrive at the same solution anyway. Okay. So, that is what will happen here. So, if you see the total response, it consists of forced response due to the input primarily, this is because of that, okay, and there is a natural response which is due to the energy dissipation and all that actually, you can interpret that way. And if you really look at the transfer function, the way it is manipulated and all that, you can visualize that the pole of the input function generate the form of the forced response. See, here it is very clear, pole of the input is 1 by s actually, right, because s was like input was 1. So, the pole was s equal to 0, and that is what led us to forced response actually. Similarly, pole of the system, I mean system transfer function, it generates some sort of a natural response actually. So, this part is forced response, that part is kind of natural response, and then the zeros and poles together, everything that you have to consider together, which will dictate the exact nature of the response, including the amplitude, how much it will go, where it will go, number wise, it all matters, and the zeros also play some role, which we will see towards end of this class actually. Alright, and now move on, I mean moving on further, we can see that this transfer function what we have here, in S plane we can represent something like this, okay, because see this transfer function was something like this, 1 by s plus 2. So, in general I can put that as alpha, s plus alpha sort of thing. So, the pole location is at minus alpha. Okay. So, pole at minus alpha generates the response something like that, k into e to the power minus alpha t actually. Okay. So, what does it indicate really? So, that all poles should lie in the left half of the S plane, it essentially leads us to e to the power minus alpha t, some sort of a function in the time domain, and that is stabilizing term anyway. Okay. So, because of that we kind of guess here that for system stability all poles should lie in the left half side. Now, that is at this point of time I will consider that as a simple kind of guess we are doing, later we will show why it should happen and all that actually. Even for MIMO system, even for I mean linear MIMO system of course, otherwise you cannot talk about poles. Then even in that case all poles should lie in the left half plane, I mean that is the result actually, but we will see as we go along with that. In general, the first order systems we can discuss like this, a by s plus a. So, this is and purposefully we have written a and a here, there is a reason for that. If you have b here, then you write it as 1 by b, sorry b by a into a by s plus a sort of thing, and this b by a will turn out to be some sort of a gain multiplier basically. Okay. So, that gain multiplier aside, we are left out with some standard form a by s plus a basically. Okay. That is what we want to analyze. The pole location is obviously at minus a. Okay. And 1 over a in this form, okay, is nothing but the time constant of the system. Some of that we already saw that in the last class also basically. Okay. So, and for if you really consider a unity step response, that means the input is 1, then we have C of t is in this form actually. Okay. 1 minus e to the power minus t by tau. That is what unity step response is all about actually. Okay. So, essentially again if you see the nature of the function, nature of the curve, this will be something like this, you have 1 here. Okay. starting from whatever initial condition, you will go like this exponential way actually. Okay. And remember, as t goes to as t goes to infinity, then this part goes to 0. That means you are left out with 1 actually, and that is primarily because of having a by a here. If you have b by a, that may not happen. That we saw that last class also basically. Okay. So that's that's one of the reasons why you want to consider this some sort of a by s plus a basically. Okay. So this is the time part of it. Sorry. Okay. So this is the time part of it, and this is C of t actually. What you have here is C of t, and what this is essentially the input part of it actually. Okay. Anyway, so if you already know the response, then you can talk about derivative of that actually, that particular function, and that turns out to be like just 1 by tau at t equal to 0. So initially it will start with some sort of a 1 by tau as slope actually. Okay. So all these analysis are done for further ramification, further explanations and understanding of the solution nature. So this turns out to be in general what we saw in the last class also, that if you consider this t as tau, and then this first first t, then 2 times of the t, 3 times of the t, like that. Essentially at 4 tau sort of thing, or 4 t, we have the response which is 98.2%, and that's what we normally call that a settling time for first order systems actually. Alright, now coming to the second order system, again we go back to that, suppose we go to that RL circuit and introduce a C now, okay, and consider the Vc as the input part, Vc as the output, where V is still the input actually. Okay. Then it will turn out that Cs by Rs is nothing but some sort of a differential equation of this form, and this is again a standard form where omega n square and omega n square both appear in numerator and denominator. That's purposefully we do that actually. Something else is there, you divide and multiply, so that this one pops up from the other part of it. So omega n square appears in the numerator as well actually. Okay. And this particular form, again unity step response, the solution can be derived. You apply some sort of a 1 by s, because there is a input is 1, so R of s is 1 by s. So you do take 1 by s here, do this partial fraction expansion, it will have multiple solutions, and then this quadratic equation, assuming that it has this complex poles, it will turn out to be complex conjugate pairs, and you do further algebra and things like that, then you essentially end up with some form like this. C of t will give us something like that, where omega d is the damped frequency given in this form, and phi is the phase shift given in that form. Okay. And then depending on whether you have this zeta as 0 or in between 0 and 1 and things like that, and then you have the response that we already discussed in the last class as well actually. So if zeta is 0, it is undamped, it will keep on oscillating that way. Zeta is greater than 1, it will have overdamped sort of behavior, it will take lot of time to go there, but there will not be any oscillations at all. Zeta equal to 1 is somewhat in between, exactly at the boundary line. So but that rarely happens in practice anyway. But then zeta is 0 in between 0 and 1, which is an underdamped system, and that's what with the solution we found here actually. Okay. Alright, so now we go on to further things, then we talk about what is kind of rise times, peak time, settling time, all that I think we discussed that last class. So for example, settling time is something like if you see the response closely, and then once it enters this 2% condition or 5% condition, whatever you take it as your condition, then it should not come out of that. So it should stay within that bound actually. So the time it takes to go there is nothing but settling time starting from 0. Okay. And this is the overshoot type of thing. So the maximum overshoot it has from the reference command, whatever you are given, in this case it is 1, then MP is nothing but percentage, if you convert that in percentage, then it turns out to be percentage overshoot essentially. Okay. And in general, the poles will be located something like that. Remember, it is sigma plus or minus j omega actually. So sigma plus or minus j omega d sort of thing. So the sigma part turns out to be here, and omega d is nothing but omega n into square root of that part of it. That is the complex part of it. And remember, if there is a pole out here, there is also a pole out here. They cannot happen. Independently they cannot occur. They have to occur in some sort of a complex conjugate manner actually. Okay. So that's what the pole location all about. And then this radial distance is nothing but omega n. The distance along y axis is omega d. The distance along x axis in the negative direction is sigma. which is, and this is nothing but zeta into omega n also. Some of these things are very handy in visualizing the response behavior and things like that actually. And there are exact values available for these quantities. For example, rise time can be given exactly like this definition, pi minus beta by omega d, where omega d is already like that and beta can be defined that way. Peak time is given like that, maximum overshoot is given like that, and settling time is given like that. Okay. And these are again, as I told in the last class, these are very handy in design as design tools also, including linear as well as nonlinear systems. So, it makes sense to remember some formulas which can be remembered very easily. For example, settling time is 4 by zeta omega n, assuming 2% criterion, comes very handy. But second order systems, you have to remember at least one more thing. So, probably percentage overshoot is another thing to kind of remember that quickly. So, once you give us how much percentage overshoot we want and how much settling time we have, then we start our design process and we can actually design a control system which will satisfy these time domain conditions actually. Okay. Now, moving further, now depending on the pole locations, we will have different response characteristics, and here is the pole location which is kind of real, but non-repeated. Then there will not be any oscillation, so it will go towards like that. And suppose it is like complex conjugate pairs, then it is a classic case of underdamped system. So, it will have this response characteristic. If these two poles sit on the imaginary axis, there is no zeta part of it, zeta is kind of 0. So, it is undamped system. So, kind of okay, so it will turn out to be like this, and then this is there is something like critically damped with double poles and things like that. So, depending on you have this depending on the nature of where it occurs and things like that, you can visualize the response characteristics that way. So, it is closely related to the pole location, that the nature of response what you get actually. And then the zeta plays a role here, especially for underdamped systems. Especially for like second order systems. If zeta is 0, it turns out to be like this, and this is we already saw that this is undamped case. Zeta is in between 0 and 1, this will turn out to be like that, and this is like that way. So, again this you can represent, you can visualize these pole locations from zeta condition also, basically, like how much damping you have really. Okay. So, all these are kind of related to each other, and this is again the same plot elaborated in a little bigger way. So, this is sigma and j omega part of it, this is omega n, okay, and this is the zeta d part of it, that is zeta times omega, sigma d part of it, that is zeta times omega n with a negative sign. And this is the omega d part of it actually. So, given a pole location, we will really know how much is omega n directly basically. If you simply consider the distance, just a Euclidean distance between origin and that pole, then this is nothing but omega n essentially. And if you know this projection essentially, that where it cuts and how much is the x axis, and once you know omega n, you can find out zeta also basically. Okay. And then we can see interesting ideas here, that what happens if the poles start moving away and moving away in a particular direction, let us say. So, for example, if it moves away in vertically away, in other words, this j omega part of it keeps on going to plus or minus infinity, where the sigma parts remain same, then the response characteristics becomes like that. In case 1, it will be something, if it is like that, then case 2 will be like that, and case 3 will be like that. Okay. So, what you observe here, the moment it goes away and away, you are introducing more and more oscillations in the loop. The frequency component keeps on becoming higher and higher actually. Okay. Similarly, if it goes away in the parallel to the x axis or parallel to the sigma axis rather, then it turns out that okay, if it is 1 corresponds to that, 2 will correspond to that actually. In other words, you will have more zeta in the loop, more damping in the loop actually. So, it will turn out to be kind of a more damped sort of thing system. And if it goes radially away, the omega n remains constant basically. So, you can see this 1, 2, 3 will correspond to 1, 2, 3 out here actually. Okay. So, right, this is with the constant real part, this is with the constant imaginary part, and this is with some sort of a constant damping ratio, because this cos theta is nothing but zeta also. So, the angle remains same, means zeta remains same, the damping ratio remains same actually. Okay. Now, what about adding a pole there? That means we already analyzed the second order system. What if we have a third order system? Then again, depending on where the third order system, where the third pole is, we consider it as some sort of either near to the dominant second order pair or far from the pair or at infinity, either way. Okay, then what is the implication? If you see case 1, case 2 and case 3, the response behavior is something like that actually. Okay. And remember this case 3 for example, this is a classic second order system actually, because there is no third pole here. It is really at infinity sort of thing. So, compared to second, if you consider case 3, then case 2 and case, what is that, case 3 is the ideal case, then case 2 and case 1 are a little far away from case 3 really. And how much the response is away from this plot depends on where this pole is located actually. Okay. The moment this pole is located not really at infinity, but still considerably far away, it is close but not very close enough actually. So, that means there is a residual response which is coming because of the third pole actually. And if it is coming real close to that, then these two will go away from that. That means the residual will be larger actually. Okay. This is actually like a third order system. The second order approximation is not good here, whereas this is kind of okay depending on your application, and this is a perfect second order system. So, the message here is the third pole should not lie close to the dominant second order pole. If it lies close, then the approximate second order system will not hold good actually. Okay. So, what is this effect of adding a 0 in general? These are all adding a pole, that means the third order system, fourth order system, fifth order system like that. And when you talk about classical control system, and especially this PID design and things like that, which is like we will see that in a very quick way also. Proportional integral derivative sort of control, PID control, which is very popular in both in literature as well as practice. They all talk about accounting for the dominant second order poles actually. That means anything that is away from this poles are kind of neglected in the design process and all. And from variety of gain tuning and simulation and all that, you assure that the design is okay basically. So, the whole idea here is, if it is a higher order system, I will consider as some sort of a dominant pole kind of idea, and then still considered as an approximate second order system for my design purpose. Okay. So, that kind of ideas are available, and that is but how much you are away from the reality and all depends on how much away your third pole is actually. Okay. Now, how about adding a 0 term here? Okay. Now, this is all about pole location. We have been discussing about pole movement both in y direction and x direction, radially, all sort of things. We have been discussing about pole location and things like that. And we also saw briefly what happens if we add a pole actually, like second to third order, third to fourth order like that actually. Then the next question obviously is, what about a 0 effect? Does it play a role at all or no actually? Now, as we saw that previously, the zeros and poles together dictate the exact response. That means the stability behavior is dictated by pole, that is okay, but what kind of response you have, exactly where it goes, where it starts and things like that, zeros do play a role, because they also affect the residues. And what are residues? Residues are nothing but the constants in the numerator in the partial fraction expansion. So, we did this partial fraction expansion some time back. If I can quickly go there, let me see if I can, okay, here. This kind of a thing. The moment I do this partial fraction expansion, the exact value of this a and b depends on what you have in the numerator also. Suppose instead of 1 I have s plus 1, then things will be different here. A and b will be different, because the s plus 1 will pop up here, and then it will be, here it may or may not matter because s is 0, but here it will matter. S plus 1, then let us say not s plus 1, probably s plus 5, let us say here, then everywhere it will matter actually. Okay. Because it will be s plus 5 divided by s plus 2, this will become 5 by 2 really. Okay. Something like that here actually also. So, the exact value of these constants that you are getting here, the 0 does play a role here. Okay. So, that is what the message here. Okay. So, zeros mainly affect the residues. So, then the constant in the numerator of the partial fraction are affected by 0 locations as well, and hence the exact value of the response and all that actually. And the another observation is, closer the 0 to the dominant poles, okay, the greater is its effects on the transient response. Okay. That means 0, if it is close to the dominant pole, it will have more effect on the transient response as well actually. If it is far away, probably you can think, okay, it's as if it is not there, but if it is close to the dominant pole, it will have an effect for sure. Now, let us see that in a little analysis sense. Now, let us assume that C of S is the response of a system with unity in the numerator. That means, there is nothing in the numerator other than just 1. Okay. That is what C of S, the response of the system in Laplace domain, that is C of S. Then by adding a 0, the Laplace transform takes this form. That means, this is with 0, that is the response that you are supposed to get actually. Okay, like A plus S into C of S. So, that means, okay, this entire, because this Laplace transform also satisfies this linearity kind of ideas there, I mean linearity rules and all. So, this is essentially nothing but A times C of S plus S times C of S, and A times C of S is nothing but a scaled version of the original response, and S times C of S is nothing but derivative of the original response. We have seen that actually. Multiplication of S is nothing but derivative, and A is just gain multiplication sort of thing. Okay. So, if A is small, okay, that means this term is kind of not there. Okay. Then what happens actually? If A is really small, then this plays a major role. That means, the derivative term becomes predominant, and remember, if it is some sort of a let us say step input response that you are talking about, this is the type of response we are dealing, right. I mean, we have some response like this actually. Okay. That means, the derivative is also positive in the beginning. The value is just, I mean, this value what you are expecting is positive anyway. Okay. The derivative is also positive in the beginning actually. Okay. So, that means, okay, I don't know. So, that is what is going to give us some sort of idea actually. So, if A is small, the derivative component is plays a more important role here, because derivative is also positive in the right direction, I mean in the same direction sort of thing. It will lead to some sort of more overshooting. Okay. The overshooting that you expect is more if this A is less compared to this term actually. Okay. That is what you see here. With no 0, that is the response actually, and with 0 equal to minus 3, that is the response, but 0 equal far away, that is minus 10, that is very close to as if there is no 0, minus 5 little far away, minus 3 even further away, like that actually. Okay. So, the more it is closer and closer to the kind of origin, then the response becomes more and more overshooting behavior basically. Okay. But that is all about in the left half S plane what happens actually. Now, what happens in the right half S plane? If you have a 0 location in the right half S plane, even more interesting things happen. So, let us see that part of it. So, if it is the right half side of the S plane, then we have something like A minus S into C of S in the numerator. Okay, because S equal to A will turn out, and A is positive here. Okay. So, again similar way it will have a kind of a scaled version, but here this is not plus, but minus actually. Okay, minus of the derivative quantity. So, that means, if the derivative term is larger compared to this one, okay, because again this is okay, previously it was plus actually here. So, both are kind of adding to each other. Now, here it will be minus to each other, I mean they will kind of counteract to each other. So, if this term is larger, okay, compared to this, then what will happen? Then the system will initially follow the derivative, but in the other direction. So, this is the direction that you want to go, because this is simply a scaled response actually. Okay. But this will pull you in the other direction, because derivative is also positive, but it will act in the negative direction actually. So, essentially it will have some sort of a negative response in the beginning. Okay. Right. And then you will have I mean that is what the picture, I mean the message tells here. If a negative response in the beginning because of the derivative, but eventually this will be powerful. So, then it will turn out to be like that actually. Remember, as t goes to infinity, as time evolves, then this derivative component also becomes 0, because of see this response what we discussed here. Okay. If you have some response like this, then initially it is very high, but then gradually it becomes, the derivative component becomes 0. Okay. So, derivative components really do not play a role after some time. So, as time evolves, that loses significance actually. but initially it will show its power. So, that is why you will have initially it will be a negative response and then it will turn out to be positive response. And typically these systems are called non-minimum phase systems. Okay. And for classic example is like tail control aerospace vehicles. Most of our airplanes are typically tail control because of maintaining nice aerodynamic behavior and things like that. But the moment you have a tail control, the mechanism turns out to be like you have to, suppose you want to go up, then first you apply a force downward, so that the vehicle will rotate, something like that. Okay, then they will have a more force, so then it will go up actually. Okay. That means initially you are applying a force downwards, which is acting on a rigid body. That means the entire body will drop down and then you kind of moves up actually. The force is like this. So, it will go a little together down, but simultaneously this is also rotating, and then it will show a large angle of attack. It will have more lift and then it will start going up actually. So, that is what normally it happens actually. So, most of the tail control aerospace vehicles are typically non-minimum phase systems, and non-minimum phase systems do play a very important role for when we discuss about inverse dynamic based control design. That means, if you really talk about dynamic inversion or feedback generation sort of ideas there, then non-minimum phase systems are very critical. In other words, the pole will become 0, 0 will become pole, all sort of ideas we will see later. And then if you have a, this is actually a pole in the right half plane, remember that. So, I mean 0 in the right half plane. So, for the internal dynamics later, that will turn out to be a pole in the right half plane, and that is disastrous actually. That means the internal dynamics will really behave in an unstable way, because the 0 will suddenly act like a pole there actually. Okay. So, all these things we will see as we go along. So, these little things what we are studying here are also important for nonlinear control design later all the way. So, with that message probably I will stop here for this particular class. This is kind of an overview for time domain response and all. We will see little more further things in the next class about some different concepts of classical control theory, including stability behavior, root locus plot and things like that actually. So, next couple of classes will be on classical control seal, will not move away so rapidly. So, with that I will stop here. Thank you.